Good afternoon and welcome you all for today's lecture. This is lecture number 3 for solar energy and its application. And topic for today's discussion is what is a transmissivity and absorptivity of the solar. So here we are going to discuss what is a transmissivity. Transmissivity is a very important parameter because when solar radiation comes on the cover plate, it will be transferred, it will be transmitted from the cover plate to the observer plate inside the solar collector. So higher the transmissivity is a desirable outcome. So we have to select the material and thickness and number of cover plate in such a way that the highest percentage of the incoming solar radiation will be transmitted to the observer plate so that we can optimize the performance of solar collector. That's the purpose of the finding out transmissivity of the solar collector. So let us discuss transmissivity. First, transmissivity. Solar collector and transmissivity of the cover plate, transmissivity of the glazing, and transmissivity depend upon two parameters. First, transmissivity due to reflection, and second, transmissivity due to refraction, and third, transmissivity due to absorption. Because when incident solar radiation falls on the surface of the cover plate or glazing, some percentage absorbed by the cover plate, that is a absorptivity. So here we have to define transmissivity tau equal to tau R into tau A, absorption. And tau R is based on the reflection and refraction. Tau R represents reflection and refraction. So let us see what is transmissivity due to reflection and refraction first, then absorption, and then we find tau as a product of tau R and tau A. Means transmissivity due to reflection and refraction and transmissivity due to absorption. So first we will discuss transmissivity due to reflection. So this is a interface. We can say this is a cover plate. This is a cover plate having some thickness. This is a cover plate, and this is a normal to the surface. At this range. So a sun rays is coming and inside. This is normal to the surface, and this is a cover plate. Cover plate or glazing. Or we can say glazing. It is also known as a glazing. It is a transparent, and you can see in your cars there is a glasses windscreen glass is made of the toughened glass. So cover plate or glazing, and radiation is incoming at an angle of theta1. If it is a incident ray IB, and falling at theta1, and after refraction theta2, and reflection will also takes place. Reflection same angle theta1, because reflection and incidence are at the same angle. Incident angle and refraction angle is the same, theta1 theta2, and due to refractive index n1 and refractive index n1 and n2, a medium 1 and medium 2. Medium 2 is simply glass, and medium 1 is air. So by Snell's law we can define. We have studied Snell's law in our physics, high school and inter physics. Snell's law, using Snell's law, sin theta1 upon sin theta2 equal to n2 by n1. So n2 means a refractive index of medium 2, and n1 is a refractive index of medium 1. And refractive index of medium 2, because glazing is having some thickness. We are not saying thickness here. You can show thickness. This is a glazing. If you want to show thickness, so this is a glazing. You say this is this thickness. You can assume thickness here del C, cover plate. This thickness, and this is a N2. N2 is a medium of the glazing or cover plate that is made of the glass. So you can assume this is a del C thickness. Del C is a thickness of the cover plate because it is not very high, 3 to 5 millimeter is the thickness of the cover plate. Using Snell's law, N1 sine theta 1 equal to N2 sine theta 2. This is equation number 1, and this equation is used for finding out theta 2. Always we have to require to find out theta 2. Now we know that due to reflection, first we are considering reflection and refraction. Due to reflection, you see there are, after reflection light is polarized, and polarization in means before incident on the surface light will be polarized like this. Only two components will remain after polarization: perpendicular component and parallel component. We are perpendicular component, and by another color we show parallel component. These are parallel components. So light will be polarized perpendicular and parallel component. So reflectivity also will be for the perpendicular component and parallel component. Reflectivity will be also for the perpendicular component and parallel component. So before polarization, here you can see, if you want to define the light, it will have all components in all directions. Before polarization of light, it will have all components in all directions, but after polarization, after reflection, it is polarized in plane and perpendicular. Means light electromagnetic wave will vibrate along perpendicular and parallel components. So one reflectivity will be for perpendicular and one reflectivity for the parallel. So first we find for the 1, sigma 1, reflectivity for perpendicular component. Reflectivity for perpendicular component we find as sine square theta 2 minus sine square theta 1 upon sine square theta 2 plus sine square theta 1. This is for the reflectivity due to perpendicular component. Now reflectivity for the parallel component equal to tan square theta 2 minus tan square theta 1 upon tan square theta 2 plus tan square theta 1. This is out of scope for defining and deriving these two equations. We have to remember, because based on the empirical and experimental observation, these reflectivities are defined for parallel and perpendicular components. And for finding out the total, you can find out rho equal to 1 by 2 average value, rho first perpendicular and rho reflectivity for second. This is, you can find out if you want to define reflectivity only for the reflection and refraction. This is for the reflection and reflection. So in this way you can find out reflectivity. So we minimize it for further. Now reflectivity based on the refraction. This is for the reflection. And now we find out, because due to refraction, only refraction component will causing radiation will reach to the observer. Otherwise, this will go surrounding into atmosphere again. Only this component, refracted component, will allow radiation will reach to the observer. That's why this is more important. But this will depend upon the rho. That's why we calculate rho perpendicular and rho parallel. Otherwise, there is no need. Because refraction component is responsible to observe, because you know that here is observer plate, and this radiation, this is observer plate, and this radiation will reach to the observer plate due to refraction. So how much refraction is reaching to the observer plate? That's why transmissivity is defined as tau r, and it will be equal to tau r first and tau r second. We have to define tau r perpendicular and tau r parallel component. So let us see, let us once again make a glass plate. This is a cover plate, and this is a observer plate. Because here how much radiation reaching, that we want to calculate. This is a observer plate, and this is a cover plate. Having thickness del. So now let us see how much radiation reaching here. Taking here first incident radiation coming here, having intensity 1. For our simplicity, we take it a 1. 1 is a magnitude, unit magnitude of intensity of the incident radiation reaching at this point having angle theta 1, and reflectivity is rho, so it will be reflected back to rho. So how much refracted, how much will be refracted? This is a reflected component, so 1 minus rho is a refracted component that is reaching to another, because cover plate has two, one top surface and one bottom surface, and again from bottom surface it again reflected by, so reflection will be equal to rho into 1 minus rho, because rho time reflectivity is rho, so rho fraction will be reflected, so multiplied, this is a incident, this is a refracted component reaching to second surface, surface 1 and surface 2. Cover plate has two surface, surface 1 and surface 2. So surface 2, after reflection from surface 2, it will be reaching to the, now using colored, this is the amount of radiation reaching to the observer plate. So how much out of 1 is in first series of the reflection reaching to the observer plate. So you know 1 minus rho 1 minus, after subtracting 1 minus rho into 1 minus rho, you will get 1 minus rho comma 1 minus rho is equal to 1 minus rho whole square. This is reaching 1 minus rho whole square. After first series, first phase, this is reaching to the observer plate, and then again it will be reflected from first surface. Again in second series, it will be reflected to the second by first surface. So after reflection, it becomes rho square 1 minus rho, and from second surface again reflected by equal to rho cube 1 minus rho. And how much reaching to the observer after this second phase? How much reaching to the observer plate? Rho square minus 1 minus rho cube 1 minus rho. You can take common, so you can simply find out rho square, and you can subtract here rho square 1 minus rho cube 1 minus rho. You can take common rho square 1 minus rho, to get 1 minus rho, so equal to rho square 1 minus rho whole square. Again rho square 1 minus rho whole square after second, and this will go on ahead. Again after this is a second, from third you can see reflection, once again reflection will take place. Third equal to rho to power 4 1 minus rho, and again here rho to power 5 1 minus rho. So how much reaching to the, after third reflection and refraction, how much reaching to the observer plate? This is so rho power 4 minus rho to power 5, again this will be equal to rho to power 4 and 1 minus rho whole square. So this is the amount of how much reaching to the, this is we have to take, because how much reaching to the observer, that is a concerned part, because this is the energy that is reaching to the observer plate after refraction and reflection, and we have to consider, so tau r first, because we are taking only perpendicular component, tau r first equal to, and here we have to show, because rho 1, we write rho 1, because we are considering only perpendicular component, so take it rho 1, everywhere rho 1. Rho means rho perpendicular, we are considering reflectivity due to perpendicular component, so can take it rho as a rho perpendicular component. That is equal to sum of all these components. It is sum of all these radiations that are reaching after refraction and reflection from the cover plate. That is equal to 1 minus rho first whole square plus rho first whole square 1 minus rho first whole square plus rho to power 4, rho 1 to power 4 1 minus rho first whole square to so on. So this is a series. This you can see, this is a series, and you can simply express this one, tau r first equal to a upon 1 minus r, that is a upon, so a upon 1 minus r means 1 minus rho first whole square upon 1 minus, here r square means r is a rho 1 square, So 1 minus rho first square. Solving this, here I think we can replace this one. So we can find here tau r first equal to 1 minus, sorry, first means parallel. This is a symbol of parallel, sorry, symbol of perpendicular. 1 minus rho perpendicular whole square upon, open this one, 1 minus rho perpendicular and 1 plus rho perpendicular. This one we replaced, so remaining value will be equal to, now we replacing this, there is no need of this now. So now replacing it, so equal to tau refraction first means perpendicular component, transmission due to perpendicular component equal to 1 minus rho perpendicular upon 1 plus rho perpendicular. Similarly, we can find out, there is no again repeating, because similarly we can find out tau r parallel equal to 1 minus, only thing that rho parallel upon 1 plus rho parallel. So this is a way, and simply you can find out tau r equal to 1 by 2 tau r first, sorry, tau r parallel component. So average of these two value will give you a transmissivity due to refraction. Transmissivity due to refraction. Here we have considered only one plate. We may use a 2 plate or 3 cover. Sometimes we use it for maximum trapping of the solar radiation. We use a 2 cover plate or 3 cover plate. So suppose there are m number of cover plates. If m is a number of cover plates, so equation become tau r first equal to 1 minus sigma, sorry, 1 minus reflectivity first upon 1 plus 2m minus 1 reflectivity of the perpendicular component. Similarly, for second one, tau r parallel component, so 1 minus reflectivity parallel component upon 1 plus 2m minus 1 reflectivity of the parallel component. If m is 1, again we get same equation. If m equal to 1, 2 minus 1 equal to 1, you will get tau r. These same value will repeat. For 2 m number of 1, if there is m number of 2, m is 2, then it becomes 3. 1 plus 3 reflectivity of the parallel or perpendicular component. This is a way of finding out transmissivity due to refraction. This is a transmissivity due to refraction. Now finding time, next we are going to find out transmissivity due to absorption. Transmissivity due to absorption. Transmissivity due to absorption, because some portion will be absorbed by the, some percentage of the incident beam radiation will be absorbed by the glazing. It become heated, so we have to minimize, we have to select material in such a way that minimum quantity, minimum intensity will be absorbed. If more quantity of the intensity will be absorbed, then that will be reaching to the absorber plate will be less, and the thermal performance of the solar collector will be reduced. So here we have to consciously select a material in such a way. That's why there is a continuous research on material of the glazing, material of the absorber plate, material of the insulation, material of the side insulation. All these is a continuous way of improving thermal performance of the solar collector. So now let us define what is a absorptivity. So this is a cover plate. This is a cover plate having thickness del C. Del C is the thickness of the cover plate. And let us see incident beam radiation is coming perpendicular at this angle. This is normal. Normally incident IB. Beam radiation is normally coming, and we take a small thickness of del X. Let us take a small thickness layer here, small thickness layer of del X. This is a del X thickness layer we are taking, and here intensity reaching up to this point is I. At this particular point intensity is, and just reaching at this point is I plus Di, because due to absorption of radiation, it will change after passing through this thickness dx. Passing through this thickness dx. This is a dx. So di, what is a di? Intensity of this change in intensity. Change in intensity is proportional to di is proportional to minus I dx. Means change in intensity. Change in intensity after passing through dx thickness of the cover plate material is proportional to initial intensity and proportional to thickness of the layer that we have taken. If we remove this proportionality constant, di equal to minus ki dx. Ki dx. This is equation number 1. And k is a extension coefficient. K is coefficient of extension, coefficient of extension, and value is a meter power minus 1 per meter. It is a unit per meter, so meter power minus 1 meter per meter. So now we can integrate this equation di upon I equal to minus k dx. Integrating this equation for indefinite integral. So ln I equal to minus k x plus c, equation number 2. Now applying boundary condition, here distance is x. At distance x we have taken thickness dx layer. Applying boundary conditions at x equal to 0. At x equal to 0, intensity of incident radiation equal to I beam radiation. I equal to, you can take normal beam, n you can add n. Normal beam radiation. Normal beam, because it is incidenting normally on the surface of the cover plate. So at I become IBN at x equal to 0. By using this equation, you can find out value of constant. Here you see here at x equal to 0, I equal to IBN. So ln IBN equal to C. Putting value of this constant here, so ln log natural base I equal to minus kx plus log natural base Bn. Bn is a suffix. B means beam radiation. So ln I upon IBN equal to minus kx. Taking antilog of this equation, I upon IBN equal to e to power minus k. I upon IBN equal to e to power minus kx. This is equation number 2. Now applying another boundary condition. Apply another boundary condition that x equal to del c. At x equal to del c, radiation that will come out equal to I. Final, suppose we denote it by IL. Then leaving radiation, intensity of leaving radiation L, because it is coming out of material. IL is coming out from the cover plate. So this equation becomes IL upon IBN equal to e to power minus k del C. Del C is the thickness of the cover or glazing. So this ratio, intensity of radiation coming out from the cover plate to the intensity of beam radiation. Ratio of intensity of the coming leaving radiation to incoming radiation is equal to, that is known as a tau A. You can denote it tau A or tau alpha, any symbol you can take. So that is equal to e to power minus k del C. So tau A means transmissivity due to absorptivity is a ratio of leaving intensity to incoming intensity. That ratio, IBM is a incoming radiation, IL is leaving radiation. This ratio of leaving radiation intensity to incoming radiation intensity normally is equal to e to power minus k del. And this can further, because in most of the cases beam incident is not come normally. So Most of the time beam radiation will like this. It will incident at angle theta 1 and leaving at angle theta. Distance traveled now equal to this distance L. L is distance traveled by the beam inside the material. So replace this here in this case del C equal to become in terms of L. How much value del C equal to? So del C become from this equal del C will become L, that is a length of the beam. L become because distance traveled by the beam is L. So L become del C upon cos theta 2. So here in place of del C we can replace because now earlier when beam is coming normally, so beam is traveling distance del C. When beam is incident at angle theta, it will traveling distance L. So L will be in terms of del C equal to del C upon cos theta 2. Del C upon cos theta 2. So replacing here tau A equal to e to power minus k del C upon cos theta 2 when incident radiation at theta 1 degree. In that case, when we have to find out theta 2 by using n1 sine theta 1 equal to n2 sine theta 2. By using this equation, we can find out theta 2. So we can find out cos theta 2. So this is for the single cover plate. If the cover plate is more than 1, suppose m number of cover plates, so you can multiply this equation. Tau equal to e to power minus m into k into del C upon cos theta 2. This is general equation for m number of cover plate. For m number of cover plate, m is a number of cover plate, m is a number of cover plates. So this is equation by which we can find out transmissivity due to absorption, transmissivity due to reflection. Already we have calculated. So tau become in this next page we can see tau become tau bar into tau. Now we can draw a graph for taking number of angles. We have taken only one angle theta 1. We can simply take theta 1, theta 2, theta 3. Suppose theta 1 is 30 degree, theta 2 45 degree, theta 3 60 degree, theta 4 90 degree. Taking all these angles theta 1, theta 2, theta 3, theta 4. These are values. So we draw a graph. How these values will vary. So take a graph between. Let us draw a graph. A graph theta 1, 0, 30, 45, 60, and 90. These are theta. And here tau r, tau absorption, and net tau. Values here 0. 0.2, 0.4, 0.6, 0.8 and 0.11. It can be never 1. So let us make a grid for simplicity and grid. Let us draw a graph. Tau absorption, then tau r, and net tau will be lesser than. If it is a general graph, so tau, this you can see by making an angle. This is a solar radius, this is a glazing, this is the angle theta 1. How theta 1? Theta. When theta is varying, theta incident angle varying, at 0 you can see when 0 angle, this angle is 0, means the beam is coming normally. You see tau, all values are maximum when theta equal. When beam is coming normally on the glazing, this is a glazing. When beam is coming normally on the glazing, most of the radiation will cross through this glazing and reaching to the observer plate. When an angle is increasing, you see the angle is increasing 30, 45, 69. These values, tau A is also, tau A means it decrease of tau, it remains almost calm because any radiation coming parallel or perpendicular, some portion will be absorbed by the observer plate. So it is not too much depending upon the angle of incidence. So absorption at transmissivity due to absorption is not too much depend upon the angle of incident, whether falling normally or at some angle. Radiation will be absorbed by the cover plate, but it will decrease. Certainly, it will decrease. But transmissivity will be become zero at 90. When radiation will come like this, angle becoming theta 90. So it will not cross through the cover plate. It will go parallel and it will not crossing because it is coming parallel. That's why transmissivity due to refraction is becoming zero. And refraction is zero. This component zero. This is a product. Tau is a product of tau r and tau a. When one component zero, overall transmissivity will become zero if incident radiation is coming at 90 degree. That's why there is a need of tracking of the solar radiation, so that always you will see in tracking type of these collectors, we track radiation in such a way that incident radiation will always fall normally to the surface of the collector. Otherwise, transmissivity will become zero or become less at higher angle, and performance of the collector will decrease. That's why performance of the flat phase solar collector is lesser compared to thermal performance of the parabolic truck collector, because these are tracking type of thing. They continuously track the solar radiation, but in flat plate solar collector there is no any tracking mechanism. That's why only manually we align the collector time to time in such a way that most of the time radiation will come normally to the surface of the collector. So you here see that what is the importance of the incident radius, what is the importance of the incident radiation. Thank you very much. I hope that this concept is very useful for competitive examination point of view, particularly Indian engineering service examination. You will find about 45 marks question, 45 to 60 marks question come from the solar energy and alternate energy sources. Means non-conventional energy sources. Other questions also come from the wind energy, ocean thermal energy, and fuel cell. So combinedly, you will get 60 marks question in engineering services main examination. That's why this topic is very important, and I am here to cover the whole syllabus of these alternative energy resources for the engineering service examination point of view. Thank you very much for watching, and please share, like, and subscribe. Thank you very much. Have a nice day.